This is part 2 of the Chapter 5 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. We're continuing with the basics of machine learning algorithms. Generalization refers to an algorithm being able to perform successfully on data it has never seen before. This is a challenge because that data might express some patterns different to what the test data shows. The problem is that the volume of test data is limited. Most types of data can have enormous variability, which is obvious if you consider pixel-wise comparison from one image to another, for example. As discussed previously, the concept of learning usually entails minimization of the program error, but that's only in the training data. Generalization is achieved in the process of minimizing the error that results from the test data as well. Statistical learning theory helps to achieve this objective in the circumstance that we don't have access to the full space of test data, that is, where we have only training data. This is a large proportion of the machine learning problems. The premise is that the training and test data come from a data generating process, meaning they're sampled from a data generating distribution. A few critical assumptions allow for more meaningful conclusions to be drawn. The first assumption is that every data point is independent from every other data point. The second assumption is that the training data and the test data distributions are the same. These assumptions make it so that the expected error for both the test and training data will be equal if the weights are set and then both the example and the test data space are sampled. This fact isn't as useful as it might appear on its face though, because the training process does not entail setting the weight parameters and then sampling both spaces. Rather, the example space is sampled, then the weights are set, and then the test space is sampled. As a result, the conclusion that can be drawn is that the test error will be at best equal to the training error, but would likely be greater. Based on the facts presented in the previous slide, the pathway to algorithm optimization has a two-pronged focus. The first goal is to make an algorithm with minimal training error. The second goal is to make it such that the undesirable gap between training and test error is as small as possible. Each of these prongs are important for overall success, and the pitfalls that exist for them have names. An algorithm that fails to adequately minimize training error is underfitting, and an algorithm that by its nature increases the error between training data and test data is overfitting. What makes an algorithm likely to over or underfit is its capacity. Capacity is the model's ability to fit a wide range of functions. If capacity is too low, a model will not fit the data well. It will be underfitted. If capacity is too high, a model will overfit the data. Capacity can be controlled by appropriately designing the hypothesis space. That's the set of possible functions that the model might select as the solution. For example, in the last video, the example was provided of an algorithm seeking an optimal solution with the hypothesis space restricted to all linear functions. By adding a term to the expression, x squared, the space is expanded to all possible quadratic functions. Since a new term is present, a new weight value must be assigned to it, making optimization more computationally intensive. And you'll note that the quadratic hypothesis space subsumes the entire linear hypothesis space, as the linear space is one where every solution has the weight value for the x squared term set to 0. So how can you decide on what capacity to select? Typically, algorithms will perform well when the model is allowed to take on the degrees of freedom equal to the problem that they are trying to solve. This isn't a simple answer though, because most complex problems do not simply have a set number of degrees of freedom. For example, how many factors go into determining the price of a house? There are obvious factors such as the measure of floor space, number of bathrooms, location, age, etc. But there could be potentially many more factors that are not simply quantified, such as the neighborhood, a large number of aesthetic measures, driveway size, garage size, backyard size, number of trees, number of windows. These are all numbers, but there could be other qualitative factors as well, and they could potentially be endless. The impact of some of these might be small, but the list goes on and on. Referring back to principal component analysis from earlier videos, these latter house price variables might be very far down the list of principal components, but they do capture variance nonetheless, and so determining where to cut off the capacity of the program is not trivial, because that does impact your accuracy. These charts show what overfitting and underfitting look like. In the first image, a straight line does not adequately fit the quadratically distributed data. That's underfitting. In the rightmost image, a polynomial of degree 9 is overfitted. The problem is that if more data points are drawn, they will fall along the parabola seen in the middle, which is the ideal model. But for those input points, the overfitted model will predict wildly different values in some areas. There are many more ways to change a model capacity than just adding new terms with weights. In fact, there are as many ways as there are models. Broadly speaking, the algorithm model specifies the family of functions in the hypothesis space that the algorithm might choose from when setting weights. Since finding the best model could be very difficult, usually the model settles for the best that it can find, so that results in the effective capacity. The most well-known method of quantifying model capacity is the Vapnik-Chervonenkis dimension, or VC dimension. Check the link in the description and you'll find a webpage that offers a playground environment for testing classification algorithms, and this should really help with the understanding of the VC dimension. It's defined as follows. Imagine you had n points, and each point could be classified as a 1 or a 0. They're classified in a binary fashion. In that circumstance, there would then be 2 to the power of n different possible combinations of those points being 0 or 1. The VC dimension is the largest number of points, n, for which the classifier can successfully perform assignments and make 0 error in doing so. The image from Wikipedia clarifies this notion. The 3 left images show 3 of the 8 possible combinations of binary settings for 3 points. The idea is that a straight line can successfully wall off positives from negatives in any of these combinations. On the right, however, you can see that adding a 4th point creates the possibility of a combination that cannot be perfectly categorized or walled off by a single straight line. There is a motivation and value to quantifying capacity. The reason to do so is to be able to make quantitative predictions about algorithm error with statistical learning theory. Generally, we can say that for any particular model that an algorithm has selected, there is some upper bound to the difference between its generalization error and its test error. Naturally, we're interested in finding where that difference is at a minimum to get the best results. That's one of the prongs of the twofold objectives we mentioned earlier. The upper bound on the difference between the two increases with algorithm capacity and decreases with the number of training examples provided. This figure from the text illustrates the general case of the impact of capacity on error. While test error might asymptotically approach a minimum, the generalization error often has a U-shape, so there is a particular optimal point on the function capacity that exists. To the left of the optimal point, the model is underfitting. To the right, it's overfitting. So far, the discussion has been around parametric models, where the model is essentially defined by a collection of weights, the values as being determined by the algorithm. To push the idea of capacity to the arbitrarily high limit cases, the idea of non-parametric models comes in. One way to make a non-parametric model is to make a model whose capacity is a function of the size of the training set. Nearest neighbor regression provides an example of this. Instead of using the training data to create some function, the nearest neighbor regression algorithm simply returns the point nearest to the input, or the label of that point, as the answer for the input. In that way, the more training data there is, the greater the capacity of the model, as it will be able to better manage and model more test data. Another example of a non-parametric model would be one where a parametric learning algorithm is stored inside of another algorithm that increases the number of parameters as needed. If there is noise or randomness in the process generating data for a model, then no algorithm could create a perfect model, one that predicts with 0 error. In that scenario, the error inherent to the otherwise perfect model is the Bayes error. That concludes this part of the Chapter 5 summary. Thanks for watching and stay tuned for the next one.